In this lesson, we will begin creating some new formulas for differentiation and integration. Before we worked with just polynomials, as well as roots, 1 over polynomial terms, and so on. We also had the trig functions. Now what we want to do in this chapter is add into this the exponential and logarithmic functions, as well as the inverse trigonometric functions. We begin with this idea of the natural logarithm function. Up until this point in the course, we have not used or defined the natural logarithm function, though you have encountered it in the past. What we're going to do is remedy the fact that the power rule for integrals does not work when n equals -1. We're going to find a power, something that we can use to deal with the x to the -1. First off, the natural logarithm function we will officially define as an integral for this course. Now, some definitions you've seen for natural log of x in the past are equivalent to this, but for the moment this is how we're going to use it. And with that said, we have something called the second fundamental theorem of calculus, which basically means that when you have an integral from a number to x and some dummy variable t, and you take the derivative of this function defined by an integral, you get the function that arrives by plugging in x for the variable. Anyway, this is a new derivative rule for us to focus on. The derivative of the natural log of x is 1 over x. Now, we have not handled the question of how to integrate 1 over x just yet, though you might have some ideas already. We'll get there. The next definition that I put in here, just to give you some idea of what it is, e. E is defined to be the value where natural log of e is equal to 1. There's a lot of different definitions of e that you've seen, but this is the one that we'll define in terms of this logarithm integral. What it turns out to be is the area under the curve, 1 over x between 1 and e equaling 1. So that's our goal. It's the number where we'll set up a bound where the area is 1. This number is irrational. You've probably heard that in the past about the number e. And we're going to use 2.72 approximately, though most of the time we'll just use the calculator or just not even calculate it at all. Just leave it as e to a power. Some things about the natural logarithm function that you should remember. First off, I mentioned the definition was the same. Here's some stuff about the natural log function. Here's the graph of it. It's increasing and concave downward. It's continuous. The domain is 0 exclusive to infinity. It's not defined at 0. There's a vertical asymptote there. The range is -infinity to infinity. And the function's also 1 to 1, meaning it simply passes the horizontal line test and thus can be inverted. More on that later. There's some properties of logarithms that you've seen in the past, and I'm just putting these here for us to use in problems. So the natural log of 1 is equal to 0. That is the way that the natural log is originally defined. If you think about it, the integral would be from 1 to 1, so of course that value is 0. The natural log of a product is the sum of the natural logs. The natural log of a quotient is the difference of the natural logs. And the ever popular reason that natural logs have been around is that a power inside of a natural log can be brought in front. We'll use some of these properties a tiny bit later. Let's focus on finding some derivatives with our new rule. Remember, our new rule is that the natural log of x has derivative 1 over x. But that doesn't mean that we can just say it's 1 over x for any of them. We can couple it with other rules. We have the chain rule, the product rule, and the quotient rule. This first one uses the chain rule. Or we could actually use a little algebraic shortcut that I'll show you in a minute. F prime of x, we think of this like natural log of u. So the derivative is 1 over u, which is 5x, times the derivative of our inside, the derivative of our u, if you like. So the derivative of 5x is 5. Canceling these out, we get that the derivative is 1 over x. That's kind of strange. The derivative of natural log of x is 1 over x, but yet the derivative of natural log of 5x was also 1 over x. Here's an alternative reason why. We can use the product property of logs to write this as natural log of 5 plus natural log of x. And then f prime of x would simply be, well, the natural log of 5 is a number, so that derivative is 0. And natural log of x is 1 over x, and there's our answer. So we get 1 over x that way also. This way is really a little bit easier if you remember the algebra rule. With that said, the natural log of a number times x will always be 1 over x when you take its derivative. Now the next example still uses the chain rule, but this time we're going to have to use the chain rule and there's no shortcut regardless. This cannot be split up. In general, you've got a rule for the natural log of a product, a quotient, and a power, not a sum. There is no such rule. We've got like a natural log of u here, so the derivative is 1 over u times the derivative of the inside, your u. So we get 1 over x squared plus 1 times the derivative of the inside is 2x. So we get 2x over x squared plus 1 as our final answer for this derivative. Next example. This one requires the product rule. We've got x times the natural log of x. You got a first term and a second term. Let's use our product rule. The product rule says you take the derivative of the first times the second plus the derivative of the second times the first. I just wrote all that out. I didn't take any derivatives yet. Now let's calculate the derivatives. I get 1 times the natural log of x. And remember, the derivative of natural log of x is 1 over x times x. So what happens is I get the natural log of x, and in this term the x's cancel, and I just get plus 1. Next one. This time I've got the natural log of x function inside of a fourth power. Now when that happens, it is a chain rule, but the inside is the natural log of x this time, whereas before it was the inside of the log. So I think of this like u to the fourth. U to the fourth would be 4u cubed when I take the derivative of it. So u to the fourth becomes 4u cubed times the derivative of your u inside. So I get 4 times natural log of x cubed, and the derivative of natural log of x is 1 over x. So if you want to rewrite that slightly, you could do it as 4 natural log of x cubed over x. The line right above is acceptable though. Next example. Now again we've got a natural log of something in here, so the inside would be your u. But I would recommend a little shortcut first. Take a note of this. The square root of x minus 3 can be written as x minus 3 to the 1/2. And what we know about logs is that you can bring powers in front. So this saves us a lot of trouble if we write 1/2 natural log of x minus 3. Now this derivative became much easier. Otherwise we would have had to use the chain rule twice, and that would have been kind of hard. So k prime of x equals, got a 1/2 in front. Now we've got the natural log of u. That is going to be 1 over u times the derivative of u, the inside. I get 1 over 2x minus 6. And the derivative of x minus 3 is just 1. So I really just get 1 over 2x minus 6 as my answer. Now for this one, look at this monstrosity. That's a lot of stuff in there. And this would be a nightmare to take the derivative of just using the chain rule, because you'd have to use the product quotient and chain rules on the inside of the chain rule. It would be a mess. However, let's use our properties of logarithms. I've got the natural log of x plus the natural log of x squared plus 1 to the third minus the natural log of the square root of 3x squared plus 2. Just recall how the properties of logarithms work here. If it's in the numerator, it's positive. If it's in the denominator, it's negative. Whenever I took this apart, I really took the numerator, which was all of this, minus what's on the bottom, because a quotient becomes subtraction. And then the numerator can also be split, because a product becomes a sum. Let's do one more step to clean this up by bringing the powers in front. So I get 3 natural log of x squared plus 1 And just like what we did in the previous example, we've got a 1/2 natural log of 3x squared plus 2. Now we can take the derivative. L prime of x equals the derivative of natural log of x is 1 over x. The derivative of 3 natural log of x squared plus 1 is going to have a 3 in front. Then by the chain rule, natural log of u becomes 1 over u times the derivative of the inside. 1/2 in front for the next term. Same thing. 1 over 3x squared plus 2 times the derivative of 3x squared plus 2. 1 over u times the derivative of the inside. Remember, the 1 over u is strictly because I'm using natural log, and the derivative of natural log of u is 1 over u. I'm going to simplify this a little bit, but not a lot. See, we get 3 over x squared plus 1, and the derivative of x squared plus 1 is 2x. We could write this as 6x over x squared plus 1 if we had more space. And then we've got 1 over 6x squared plus 4, multiplying through by 2. And the derivative of 3x squared plus 2 is 6x. You could write this as 6x over 6x squared plus 4 if you wanted to, and you could even cancel out a common factor of 2. Either way, this will be my derivative. Next example. This is something that we can use now that we have the idea of logarithms. This is technically implicit differentiation, but it's not hard implicit differentiation. Here's the trick. Anytime you have a function raised to a function power, you can use logs because powers can come in front. What I'm going to do is take the natural log of both sides. And then using the properties of logarithms, I can write this as x natural log of x. That's helpful. Now I can take the derivative, but again I'm using implicit differentiation. This is probably a little bit rusty to you. Just remember, for implicit differentiation, we remember that y is a function of x. The derivative of natural log of y would be 1 over y, but then y is a function of x, so by the chain rule we get a y prime. And the rule that you were accustomed to is take the derivative of the function and then multiply by y prime anytime the function's in terms of y. On the right side, we'll use the product rule. We get the derivative of the first times the second plus the derivative of the second times the first. And now let's just clean all this up. 1 over y. Derivative of x is 1, natural log of x. And the derivative of natural log of x is again 1 over x times x. So we get y prime is equal to natural log of x plus 1. And what I'm doing right here is I'm going to multiply both sides by y to get y prime by itself. Here's what we get. I get y, but y was x to the x. That's logarithmic differentiation. You take the natural log of both sides and then take the derivative implicitly, and once you get y prime by itself, you can actually plug the original y back in. This is the derivative of x to the x. You wouldn't really expect it to look that way, but it turns out to be the case. Next example. Logarithmic differentiation is also useful when you've got too many products and quotients floating around in powers. Let me call this thing y, which will help me. Then the natural log of y would equal the natural log of all this. So let's just write it out. Natural log of x cubed plus natural log of square root of x squared minus 3. We're separating with our log rules. Minus natural log of x minus 7 to the third power. When I took the log of both sides, I split the numerator into two pieces with a plus, and the denominator becomes a minus. Let's deal with these powers. So natural log of y equals 3 natural log of x plus 1/2 natural log of x squared minus 3. And then the last one is going to be minus 3 natural log of x minus 7. Now I can take the derivative. So 1 over y prime, just like last time. 3 times the derivative of natural log of x is 1 over x plus 1/2. The derivative of natural log of u is 1 over u times the derivative of u minus 3. Then the derivative of natural log of u is again 1 over u times the derivative of u. So we get 1 over y prime equals 3 over x plus 1 over 2x squared minus 6. The derivative of x squared minus 3 is 2x minus 3 over x minus 7. And the derivative of x minus 7 is just 1. So now we will multiply both sides by y to get y prime by itself. We get y prime equals 3 over x plus 2x over 2x squared minus 6 minus 3 over x minus 7, and it's all multiplied by y. Remember, y was x cubed times the square root of x squared minus 3 over x minus 7 cubed. And that's our answer. You could clean this up a little bit. It's not really worth doing. Last slide on here is I want to mention that the derivative of the natural log of the absolute value of x is actually equal to 1 over x. And what this is going to become in the next section is the actual value of when you integrate 1 over x. We're going to take this in cases. So if x is greater than 0, then absolute value of x equals just x. If x is less than 0, then the absolute value of x would make it positive, but since it were negative already, that's the same thing as negative x. And you've encountered this form of the absolute value function in the past. It's a piecewise function. It's x when x is positive, and it's negative x when x is negative. If x is greater than 0, then the derivative with respect to x of natural log of absolute value of x is just the derivative of natural log of x, which is 1 over x. Okay, so we got 1 over x when x is positive. And now if x is negative, then here's what we get. The derivative with respect to x of natural log of absolute value of x is now the derivative with respect to x of natural log of negative x. Because x is negative this time, so the absolute value negates it. With that said, we'll use our chain rule. We get 1 over u times the derivative of u. And so that turns into 1 over negative x times negative 1, which is 1 over x. There you have it. When x is positive or negative, the derivative of natural log of absolute value of x is still 1 over x. This kind of extends the rule that we had before. We'll use that in the next section.